my other screen. Okay, I hope you can see the screen. So hello everybody, I'm Michele Ongis, Technical Director of Modelta. We are a startup involved in modeling of membrane and membrane reactors. And this is indeed a membrane modeling webinar series done in the framework of the Measured project, which for the people who are not aware, is a project related to the development of innovative materials for membrane and scaling up of 3 different types of membrane, ceramic, polymeric, and carbon molecular sieve membranes for 3 different applications. So for evaporation, membrane distillation, and gas separation, respectively. Now, the project is quite complicated, so you can find all the details on the website and on the dissemination channels of Measured. We are now almost in our last year, so 2026 will be the last year of Measured, with the pilots in operation at TRL7. So stay tuned to the Measured project channel for updates. Now there are 9 countries who collaborate with this project, as I say, in 3 different lines we have 17 partners, and now the partner presenting today is the only one from Slovenia. That, for the people not trained in geography, is this very nice country close to the northern Italy, with also very nice food and hopefully very nice chemical institute. We will see today Anders presenting. Maybe Anders, you can also tell later a couple of words also about the Chemical Institute, just to know what you do. But I mean, we assume you do just the standard Chemical Institute activities. So as I said, just to present also ourselves, Anders is here today. We'll give the presentation about the CFD modeling of membranes and the National Institute of Chemistry, which is of course a very probably clear name inside the national borders, but when you go abroad, you have also to specify of which nation it is. But this is for all the countries. So I added that this is Slovenian National Institute of Chemistry, and it is participating in Measured as a responsible for the permeation and the membrane model. So to work indeed on the CFD, on the development of the transport mechanism inside the new materials developed in Measured. Then there is Manuela from PNO, and they are also the responsible for the Measured dissemination, and they are also organizing and disseminating those webinars. And then we, Modelta, are the modeling work package leader in Measured, and so we are also taking, say, the lead of the organization of the webinars. So you know all the peoples involved. Just before starting this webinar, as for the previous time, we want just to say that this is part of a webinar series. So we did the previous one on Aspen Custom Modeler. You can find the video on YouTube. Now we have this webinar about CFD, and we are thinking of planning new webinars, maybe more at process level, like techno-economic or life cycle assessment. But we also are curious to receive feedback from people about what can be interesting. So just let us know what you would like to see in the next ones, so we can also organize the next webinar. So I'm done with my introduction. So I leave the floor to Anders. Yeah, that's it. The floor is yours.
Okay, everybody can see my screen?
Yes, I can see, not yet in presentation mode.
Oh, you cannot see my presentation?
I see the presentation, but not in full presentation mode. So I see also the, PowerPoint slide, the normal.
Okay. Now?
Now we see you have to switch the display settings. Display settings. Yes, exactly. Now, perfect.
Okay. So I think most of us, we are familiar with each other. For those that they forgot my name, hey, I'm Andras. So today we have a lovely quest about the computational fluid dynamics. So here is the outline what we are going to cover. First, we will go through the CFD basics, and then I will explain a little bit one of the programs that we can use to run the CFD calculation, and that is OpenFOAM. And before you can start any CFD calculation, you have to do some meshing, so creating the computational domain. And for that, I'm going to explain two programs that is called BlockMesh and SnappyHexMesh, which is the subprogram of the OpenFOAM. And then we will cover how to use the ParaView program that once the CFD calculations are finished, we can then visualize them. So first, we go to the basics of the computational fluid dynamics. So which equation we need to solve. Those equations are called Navier-Stokes equations, but basically two conditions we have to satisfy, and one is the continuum equation, which simply means that no mass neither can be created or destroyed. And the second one of the set of the equation, we have to solve the momentum equation, which is basically more or less Newton's second law. So first of all, what is the obvious thing? And we all know what separates the solids from the fluid. So the simple answer is that fluids flows, but the major difference between those are that solids are rigid, so any force applied, it's immediately reacts into the momentum. So here in the fluid dynamics, with the fluids, it's not just a case. So the fluids like to react on the forces also to deform quite a bit, and those deformation actually then defies those equations of Navier-Stokes that we have to solve. So we have two different fluids. One is liquid and one is gas. The major difference between those is that the gas are compressible. This a little Navier-Stokes, but for a majority of the problems that we have to solve, we also can treat gas also as an incompressible fluid. Here, I want to just point out a few variables that we come across when we are doing computational fluid dynamics. So one is density, and that quite important thing is the viscosity. But as I said, most of the time we can treat the fluids as incompressible, and for that it is nice to define a new variables, which is kinematic viscosity and kinematic pressure, which is basically both of those variables just divided by the density itself. And the other thing that is quite important that divides from the laminar flow to the turbulent flow is the Reynolds number, which is basically the ratio between inertial forces and viscous forces. So a little bit more to the detail of the Navier-Stokes equation. First, we will focus on the continuous equations. So here, as I said before, we have to satisfy that no mass is destroyed or created. So what we simply do in our control volume, we actually sum up all the fluxes through the surfaces, and those have to result then in zero mass change. When we go to forces which can act on the fluid itself, you can see it's a little bit more complicated, but in the essence, we have to sum all the forces, and those actually then result that our fluid either accelerate or remains in a constant velocity. So I'm not going to go to the detail how to derive these things, but let me just mention those forces that are acting on the volume. And one is the normal stress. Those is usually related to the pressure itself. So the pressure itself try to push the fluid forward, and the opposing forces that are acting on this fluid are then the shear stress. So this is actually where the viscosity comes to play. So as I mentioned, the Reynolds number is the one that actually defines either we are in the laminar regime or the turbulent regime. So for the low Reynolds number, basically mean for the low velocity, usually then the flow is laminar, and at some point, if we speed up the flow, then we can go to the turbulent regime. Once we know those equations for the momentum, then we can also have a better idea what the viscosity is and how to measure it. So in this simple case, we have just a plate, try to move it into the x direction. And because of that, one of the conditions we always said that the fluid sticks to the surface. So at this point, the velocity at the bottom has to be 0, and the velocity of the fluid at the plate has to have the same velocity as the plate itself. Because of that, we have a gradient of the velocity field on the epsilon direction. And if we assume that the pressure is constant all over it, we have just one equation to solve here. And because this has to be equal to 0, we have the first derivative to velocity regarding the epsilon direction has to be constant. And this is simply the way, or one of the way, that we can measure the viscosity itself. So here I'm going to finish about the basics of the CFD itself, and we are going to rather focus how to use some programs that we can calculate some fluid dynamics properties. As I said here, we are going to use OpenFOAM. So OpenFOAM actually works in a Linux environment. So that is the best way, that you have a Linux system. You can choose whichever you want. And once installed, it is really beneficial that we know where the OpenFOAM is installed. We can go directly to his directory, and we can see here are the tutorials, and they cover a lot of different cases. What is this? Why this is important? Because the versions are updated yearly, and while they are updating the versions, some commands can be different from the previous version. So inside of those cases, we can always find the correct commands that we can run our specific cases. For today, I prepared one problem regarding the membrane separation. So okay. Yeah. So here is our problem. We have the simple case. We have two sides. So one is the retentate. So this is the red casing, and the blue casing is the permeate, or vice versa. It doesn't matter. It depends how you see. So in this case, we have then two inlets and two outlets. So, and in the inside of this apparatus, we have our membrane, and here the separation comes into a play. So those that they are more permeable, they are going to go to this side, and vice versa is going to happen on the other side of this membrane separation apparatus. Okay, but before we can go to the computation itself, as I said, is really important for the computational fluid dynamics that we create our mesh. So to create our mesh, we have two basic subprograms inside of the OpenFOAM, and that is the block mesh and the snappy hex mesh. And before we start confirming the surfaces, let's say that this car is our surface, and the opposite, the negative, is actually the representation of the computational mesh when the fluids flow. We first have to create this coarse block with the block mesh. I should start here, sorry. So we have to create this block mesh. And if we go then inside of our case, here I prepared the case membrane, which is the same folder as here. But before we are going to run the first step of meshing our domain, let me just say how the OpenFOAM arrange their folders. So whatever you need, once you create a specific folder for your case, you need 3 different subfolders. And one is 0. In this 0 folder, you can find all your variables that you're going to follow and calculate. The other one is the constant folder. Here you're going to define all the constants for the physicochemical properties. And the final one is the system itself. Here you can define, for this case, how the block mesh is going to operate. So which block is going to create, how the coarse mesh is going to be defined. You also have a folder when you're going to define which surfaces you want to snap into it. So in this case, you defined all the surfaces that actually all the surfaces can conform your computational domain. One of the important things is also the control dig. Here you actually define what is the, let's say, time step, how long you want to compute things, etc. Then you have numerical schemes. Here you can define is the first order, second order, and so on. For the solution, here you define your derivative, which mathematical approaches you're going to use to solve your system or linear equations. And this folder, what we are going to use is the subcommand of the OpenFOAM. It's called set fields, which actually generates the initial state of your computational domain. So if you go, as I previously showed to you, in the folder of the OpenFOAM, you can find a lot of tutorials. And with all those tutorials, you can see that you have 2 files, and one is clean file and one is run file. So I think that they are quite obvious what they do. If you call the subscript of all run, that means that all the commands are sequentially going to be run, that in the end you'll get your calculation done. And all clean mean actually that you go to the initial state. So actually it just erase all the calculation you've done, and you can start with the fresh calculations. Always you can open the subscripts, which is open in here. This is the all run subscript, which actually tells you which commands you have to run before you can start your calculation itself. And as mentioned before, one of these is also this block mesh, and block mesh actually creates the first coarse mesh where your computational domain is going to be created. So to run any of the commands, first you have to go to a terminal, which is directly related to your working directory, which is simply you go to your working directory and then open the terminal, which is now here. And now we can simply then start with the coarse meshing of our domain. So it's called block mesh. And if we run, we can see on the terminal that something it's been done. And we can always check our geometry with the paraview. ParaView is a program that is compatible with OpenFOAM itself. If we want to see what is going on, also the OpenFOAM has a command that you can directly open ParaView for these settings, which is called ParaFOAM. And if we now open the ParaFOAM program, directly creates the subfolder for your running case, and something went wrong. I don't know what happened. Let's try one more time. Well, this is really unfortunate. Well, before it was working, let's hope that our final computational domain can be seen. I'm not quite sure why now the program is crashing, but let's try to continue with our meshing.
There's a question in the chat that it should be in the other terminal, but I'm not sure if there's a difference between the two terminals.
No, those are actually the same terminal related to your working directory. I opened just two. I will explain why in a second. But yeah, they are the same terminals related to the same working directory. I can show one more thing. If this is going to be more stable. Okay. So now in our ParaView, we can see our discourse block mesh that we did. If I go to representation here, that we also can see the surfaces and edges. You can see that we define one specific block. Our computational domain is going to go inside of this. And we will try to conform all those surfaces that I was showing before of our set cape of the membrane apparatus inside and try to conform all those cells to these surfaces. So what is going on actually behind? So first we have this coarse mesh that I was showing right now in ParaView. And now we want to introduce our surfaces inside of this coarse mesh and try to snap them to conform into the surfaces. How the program works is that you defined how many times you want to divide the cells around the surface itself. So here is the representation. Let's say I want to have 4 more divisions and the cells are 4 more times divided around the surfaces itself. When this dividing of the cells is done, it goes to the next step. So here is the representation of the dividing all the blocks around the surfaces. And in the next steps, what the program does is actually it chooses just the cells that they are inside of the computational domain of where the fluid flows. So the car is not, in this case, part of it. We have some additional possibilities inside. We can say that in a specific area, in general, we want to have even denser mesh. So we can define another block inside that refines the mesh itself even more if we want to. Usually we do this because we are specifically interested in one specific area where a lot of things are going on. So the fluid accelerate, deaccelerate, and so on. And we need to refine those areas because otherwise the solvers might not be stable. So in the next steps, when the all cells were defined and determined, which are going to be in our computational domain, the snapping starts into a play. So that simply means that those triangles that they were inside of the car domain, they try to be snapped to the surface. And in the end, when we have this, we have a nice representation of our computational domain, which is snapped to the surfaces that we defined previously. One additional option that we can also do in this snappy hex mesh is also adding some layers. This is especially important where we are talking about turbulent regimes, because in the turbulent regimes we have additional sub-equations that we solve what is actually the gradients of the velocity to a surface, and this actually defines those friction forces that act on the surfaces itself. So now explain how the snappy hex mesh works. We can go back into our system. And the next step here, as it's called, we are going to do this snapping thing. So we run the program snappy hex mesh. Okay. This can be quite computational demanding if we have a really big meshes. So I choose this kind of the problem that is calculated really fast. So if we go again back to our para view, which actually shows everything that is going on, we can see that the first thing that has been done, as explained before, is find all the cells that they are inside of the computational domain, and in the next step it was snapping, and here we see that all the computational domain was conformed to our case setup that I was showing in the beginning. So here inside of the folders, which it was not so obvious, they are also defined inlets and outlets and so on. And now we are going to check now those folders, what is going on. So now we can see that here is also one subcommand which is override, because I didn't run this command. It was actually doing the computational domain into a new folders. So if I rerun now the snappy hex mesh with the descriptor that overrides, our computational mesh, it's not anymore in a subfolders here, but is directly transported to the constant, because of course computational domain doesn't change. So he actually pasted the last results exactly here. You can do the same without the descriptor and simply use this folder and copy it into a constant itself. So because our now computational domain is already in the constant where it should be, I can delete those things now. And we are ready to perform the initial condition of our variables. So as I said, this dictionary, how to set fields, are in the system itself. So if I open it here, we can see that we try to define all the variables that are needed. So in this case, we are trying to separate the methane from the oxygen and nitrogen mixture. So we define all the concentration profiles inside of our computational domain for the permeant and the retentant site separately. So if we now run these set fields, just before I run it, let me show what it's going to do. So for now, in the OpenFOAM, if you see that specific variable is labeled by .oric, which is original, this is not actually the part of the variable that OpenFOAM takes it and try to calculate. Here is just the initial thing that we define all the boundary condition and the concentration, but then with the subprogram set fields, we can actually change all those concentration inside. So what the set field is going to do, he's going to check all these original files and try to rewrite them. So if we do that, now you can see that from the Mente original, also the methane variable directory was also created. And this is actually what the OpenFOAM is going to be used in the end for its own calculation. So this is the variable that is going to be followed. Anything labeled with the original, this is not going to be part of the calculation. If we check all the other variables that they are inside in the 0 folder, we can also see that here is the epsilon and k, which indicates that we are going to use Reynolds average solver for this problem, and specifically chi epsilon, which is solving additional 2 equations to represent the dissipation energy because of the turbulence in itself, and this then impact into the viscosity and the pressure drop itself. If I now again reopen which commands we need to run, we are in this state. So we set our fields. We prepare all the case ready now for our calculation. And simply we have to run now our applications. So when you go to the tutorials and you go inside of this all run script that is going to be run, it simply says run the application, and then it says get the application. So you actually don't know what is going on. But here, if we go to the system and control dict, the application is defined here. So the application that the solver that we are going to use from the OpenFOAM is called foam run. And you can see here, I'm trying to call from the terminal this command foam run, but those other things here that they are written, it says something like that. So this is telling me that please, everything that is calculated, please pass it also to the terminal itself so that I see which calculations are running in the background, but at the same time also write a file called foam run log that everything that also I can see from the terminal is going to be written in our working directory, which is here. Why we want to do that? Because when you're running CFD, you want to follow your residuals. So residuals simply mean that it's checking how the convergence of the continuity is going on. Is there a change in a velocity field, and so on. And when everything is in steady state, if the problem we want to force it to the steady state, that means that all residuals have to drop drastically from the initial conditions. So usually for the OpenFOAM, let's say we can use the conditions that we want to drop our residuals to the power of -3. You can also use the harsher conditions. That is always depends of your system itself. Sometimes you don't want to follow just residuals of the velocity or the pressure and so on, but some more physical thing. Let's say if we have a mixing reactor and we want to calculate the torque of the impeller inside, what we want to follow is the torque itself, and when it stabilizes it, that means that we are actually at the steady state conditions. So when I'm going to perform this command foam run, as I said, here we are going to see all the things, and as the solver applies, that before you can run this application, there are a few things that they are not defined yet. So why he doesn't know what to run? Because now the whole computational domain is as one. So what I mean by that, if this is going to work, if we go here to our representation of membrane separator, the whole computational domain is fused together. So he actually doesn't know that here is the membrane itself. So if we want to do that, we need to create a baffle. Baffle simply means a surface with zero volume, but it has two different sides that it communicates with each other. So the outer surface of this is communicating with this computational domain, and inner surface is communicating with this domain. So what we want to do is then create this baffle, which is we simply do with the command create baffles. And again, we want to overwrite thing that directly go into the subfolder that it needs to be. And now we have created our membrane. It's inside of our computational domain. And if everything is done correctly, now we can finally start with our computations. So if again, now I run this foam run command, we again have a problem. This is one of the drawbacks when you're using OpenFOAM, because you're always working just with specific directories, and if the set of commands were not done properly, then simply the case will not work. So what I'm going to do first, I'm just going to clean my folder and try actually to run all the commands again in the right sequential order. So we create our block mesh. Now we create our snappy hex mesh, which conforms to the surface. We create our baffles, and now it everything is okay, the application should start running. Still something is wrong. I'm really sorry for this inconvenience. When I have a test trial, everything looks fine. Okay. Now it works. So what was the problem? When I was running this sequentially, one of the patches, I mean the surfaces of the inlet and outlet, they were not properly communicating. So I again run the right sequential sequence, which is directly following those things. And now we prepare our case to start our calculations. So as I said before, our command for running this calculation is called foam run. And what we are going to do is to print everything on the terminal, what is going on. And at the same time, we are going to log everything is solved into the terminal, also into our file. And you can now see that a lot of calculation is running in the background, and we are creating a new subfolders, and those numbers are actually represents the seconds that of our calculation itself. Because we are solving this in transient system, that simply means that we have our initial state, and through the time we try to see what is going on with our membrane separator. You will see that our calculation is going to be stopped when are going to be reached 10 seconds. That was actually defined previously into a system. When the calculation are going to finish, I will show it again. Yes, so it starts at the 10 seconds. So let me check where we defined that. So this was in a control dict. If we now open this folder, what we said that please start our calculation at 0 time. So this is our folder 0, where we defined all the initial and boundary conditions. And then we define when is the end calculation, that is 10 seconds. And our time step, it was 1 to power minus 3. So now the question was why to have two different terminals? While we are running calculation, I said that we can follow our residuals. So for now, I'm going to, again, erase all the calculation I have been done, and again, rerun our calculation from the 0 time. Because while doing that, I can use a different program called GNU-plot, which is almost always the part of the Linux system. And in this GNU-plot, I'm actually reading this folder that, directory that I'm writing everything that I can see in the terminal. And from this, I then actually extract all the number of the residuals of our calculation. And here I can see our plot. So we start at the beginning, and if this residual drops, that means that we are approaching to our steady state conditions. So this is the one more functionality that I wanted also to show. So the program that we are using is called GNU-plot, but for the GNU-plot, we have again subscript that actually tells what you want to do. So here the script says, please try to read this foam run log that we are logging everything that it was shown in the terminal. And in this line, it says, takes all the residuals that is actually related to the x direction of the velocity, then it cuts out the right parts. So in this case, if we can see our solver, so here it starts solving the x direction momentum, and we want to scrape the initial and the final residual of the system, and then we actually plug this into this our subscript, and the plot that you're seeing, we are just plotting directly those numbers into into this terminal, this image here. Okay, so now our calculation are done, and we want to see what is the result. So, as I said, the command to see your result is called parafoam, which actually opens the paraview itself. You have two different possibilities to call this paraview. One is called parafoam, and the other one is called parafoam built-in. What is the difference? So with just parafoam, you can see only calculation run in a single core, while sometimes to speed up the calculations, you want to separate your computational domains into different sectors, and with the command built-in, then we have this possibility to combine all the calculation from different parts into one mesh together to see the complete picture of our calculation. So for now, we are going to try to use just a single core because we were calculating this on a single core. But before we have a problem to visualize this, so I hope now everything is going to be fine. Yes. So now we can already see our computational domain. It's labeled with different colors that represent different surfaces that we are calculating. So here inside, there are different things that we can do. So we might want to include sets and include zones. What that means that we might to specify the specific computational region that have his unique name, and then we can isolate just those computational cells to represent it. And on the bottom, it's all the fields that we can represent. So for now, it's just reading temperature, velocity, and pressure, but we are not so much focused in those for now, but just the concentration of our gases that we want to separate. So here at the label time, we can actually start following all the calculation through the time. So first we need to select the gas we want to follow, and directly also with the color scheme here, we can see what is the concentrations. What I want to show here is then true functionality of the paraview. Here in the mesh part, you select all the things that you want to upload into your program. So the best thing is always just to upload everything that you want. So I did that because I want to extract just specific block of our computational domain, and this is pipe. So how did I do that? The functionality here is to open our functions that we can using inside of the paraview is just simply press ctrl and space, and it opens this command, and then we want to call specific function called extract function. But before, of course, we have to be in on the right subfolder on which we want to run this operation. So this operation we want to run on all the computational domain that we uploaded. So here we can extract now just our pipe domain here. So okay, we done that. And here we can just represent what is going on to inside. So we have here the functionality just to cut our domain on half in this case, and we simply have the representation what is going on in the pipe itself. So now if I click it like here, it looks like nothing is going on. I can go to the nitrogen. Here we can see some polarization. But what is the drawback if you are calculating with the infinity thin baffle? So that means this membrane that I was explained earlier, that we use baffle command to create it to separate two computational domain. The ParaView is always interpolating the values through the whole computational domain, so it's not a nice visual representation of what is going on. This is just an initial condition. Because we were in time 0, we can go directly to the end time, and here we can already see what happened to our other fields. Okay, so here in this result, we can also follow the polarization itself. Let's go to the nitrogen that we saw that some polarization is happening. It is. And if we run it then from the beginning, because the visual cannot follow that fast, then it looks like it's blinking all the time. But anyway, here we can follow for each time step separately what is going on with our system. And what is here the point of this calculation is that we can see that we have a polarization at the membrane itself. And this actually hinders our performance. So when we are designing those things, we need to have in mind specific either operation condition that this is not going to happen, or constrain all those things with the geometry. So simply meaning if we will reduce the radius here of this pipe, the radial polarization would be much less pronounced. And from this sense, our membrane is going to actually perform much more efficiently. So more or less, we are also quite, we are running out of the time. This is what I presented for today. So if there is some additional question, now we are open for the discussion.
Yeah, now, thank you, Andras. Of course, if there are questions, you can write it in the chat. Just to clarify a bit better, maybe also for people who can look back at the video, in the chart that you show, now I got that there are 3 chemical species, but just to clarify, so in this permeate side, you have a sweep gas that is going from the bottom to the top.
Yes.
Okay, because just to.
Yeah, here is not plug, but we are actually sweeping gas. That is true. And here the separation is not pressure driven, but it's concentration driven.
And this is also another curiosity, maybe also for time to put myself in the shoes of people who is the first time using this. So where you defined, or how do you define the transport equation in this case? So inside all the application you imported and you showed, where is this customizable, let's say?
Transport equation for the membrane or for
For the
all
membrane,
the
yeah.
fluid? Yeah, okay. That is directly to the point, yes. So where is defined is actually for each species. If we go to check inside, first we have to go into the 0 folder. But I'm going to go here, the original, which the initial concentration are not populated. Yes. So here, the baffle where the membrane lies is called membrane sleeve. So, and here we actually define how we are going to treat our mass transport through the membrane itself. For this, OpenFOAM already write one of the functionality, this called semi-permeable baffle mass fraction, and that is driven only by the concentration. So if you want to do the pressure driven thing, so you need to adjust those equation by all needs or whatever you want to do. So let's say that the mass flux is then defined by the pressure difference and the permeability itself. Inside of this equation, you are going to define, please check the pressure on the one side, please check the pressure on the other side, then calculate the concentration, the partial pressure, multiply this with the permeance, and then you will get the flux. And once this flux is calculated, what is going to do is going to alternate actually the velocity field. So here in the velocity field, you what is going to do here is the boundary condition then called species transfer velocity. That simply means that it checks those fluxes that they were calculated with your model of the membrane of the fluxes and adjust the velocity field at this specific surface at the membrane itself. So if something goes through the membrane, that means that the part of the fluid is actually transferred to the other side. And according to this, at the boundary that is not zero condition, actually no slip condition for the velocity, but in the direction of the transport, there is defined a specific velocity that goes outside of your, let's say, retentant side. And according to this, also then the velocity field is changed.
Okay, thank you for your answer. I see people leaving because we're out of time, so I don't see any particular additional question on this. So let's just see if some comment pops up or pops up also in my mind just to ask you, but otherwise, of course, we just collect those informations. No, I don't see other questions. Then okay, then I think well, thank you, Andras. I think it was a very valuable insight, and so it's difficult to merge the simple and general description of CFD of a software with the case study. So, but I'm sure this will be very helpful for anyone that has to work with this type of problems. Well, if there's anything else or any comment, we will see under the video when will be uploaded on the measured channels. We will let you know the questions under the video, and hopefully Andras will be also available in the future to answer some of these questions. Then thank you all the people for joining, and well, we'll keep in touch.
Okay, so have a nice day.